Hi, this is ET370, lecture 2. This is going to be another two-part lecture. In this first part, we're going to go and introduce Zener diodes. We'll talk about the symbol, IV curve, hydro analogy, and look at this, again, load line analysis tool and finish it up with an example. And the second part, we'll go into ideal diodes. But let's start with Zener diodes. So Zener diodes, they're essentially a diode, but they're designed typically to operate in reverse bias. And so they're very useful for voltage regulators. In the last example, we'll talk about that. And the symbol looks very, very similar to a normal diode in that you have your little triangle arrow thing going on. We still set up the, what do you call it, the reference current and the voltage polarity directions consistent with the normal diode. The only difference here is the bar here on the cathode has these little extra lines here. Okay, so this lets you know that's a Zener diode. Now the IV curve in the forward bias looks the same. So you have some forward voltage here, and then this is rises, right? And typically this is much steeper than drawn, but it's exaggerated just so that you can see what's going on. Now the interesting part about the useful part about the Zener diode is it is designed to actually break down at some specified voltage VB. Okay, and this is designed to be constant, very steep fall off. And what you notice is if there's any reverse bias voltage past this breakdown voltage, it will just allow current to flow. Okay, so let's look at a hydro analogy. And what I want you to think of is a pressure relief valve. Okay, so here we have a simple drawing here. And if you recall from the previous lecture, the diode has basically, it's a check valve, right? And so it'll allow current to flow in one direction, but then it was blocked, okay? And so the difference between this and the diode is that I have the spring-loaded stopper. So if you can imagine, if I had pressure here on the cathode side, this spring-loaded stopper will hold it, and eventually will let go and allow current to flow in the reverse direction, right? So ID would be negative if VD is a large enough negative value, right? So just to repeat the forward bias, it's equivalent to a normal diode. And in the reverse bias, initially current is blocked by the spring, but then current flows after a certain pressure is reached. And that's what you're seeing here. Okay, so I hope this little hydro analogy helps your intuition. Okay, so what's the mechanism that's going on in this reverse bias? Well, we talked about the forward bias mechanism in the last lecture with the holes and electrons and the doping. The reverse bias situation, why it allows current to flow is one mechanism is called quantum tunneling. Okay, and I was like, I'm not really an expert in when it goes down into this low level, and so it's a little bit of PFM, right? So you kind of almost have to hit that make believe button, but basically what it requires is that thin depletion region, right? And if you recall, that depletion region is that little area in between the p-n junction where some of the electrons have joined the holes, and so you get this positive negative, right? Okay, so if you have a very thin depletion region, remember that's kind of like a resistive thing that you got to overcome. What happens is, and if you get a large enough E field, an E field is defined as force per charge, and it's also the same as volts per meter. And so what this allows you to do is you can get a lot of force per charge if you have a very thin little distance here, right? So for the same amount of voltage, right, you get a thin distance, you get a lot of force per charge, which means you get a large E field, which means you can enable this quantum tunneling effect, all right? And how do you achieve that? You dope a lot more. You have some secret sauce that the manufacturers figure out on how to dope it. And you can get this Zener diode behavior, and they figure out how to tune it exactly so that at the right breakdown voltage, it allows this current to flow. Okay, it's kind of like tuning the spring constant, right? Okay, and so they can make this occur at low voltage, and they call this the Zener effect. So pretty amazing discovery, I would say, right? Okay, another way that this reverse current is allowed is called avalanche breakdown. It's another mechanism, right? And so the idea for avalanche breakdown is if you have a reverse bias, you get some electrons that actually move with enough kinetic energy, they move and smash into covalent bonds, and they smash into more covalent bonds, and they release more electrons, smash into more covalent bonds. So you get this avalanche effect, right? Now, both of these mechanisms don't destroy that PN junction, but the heat generated could, right? Just like in any case, right? You get too much current through these things, they get hot. With enough heat, boom, burns, okay? But yeah, this is just the tip of the iceberg of what's going on, right? But really, I think the intuition is pressure relief valve, okay? Okay, so let's look at just a very simple example. So here's like a homework problem, right? Draw the I versus V curve for something like this. And what do we notice? We know two back-to-back diodes here, but one of them, this B diode, is a Zener diode. If this was a normal diode here for B, this would be just like an open circuit, right? Because if I had a voltage here that's positive, yeah, it'll go through A, but then it'll get blocked by B. If voltage is negative, it'll go through B, but then gets blocked by A. However, this is a Zener diode. Okay, so let's kind of walk through this. When this voltage is, imagine this voltage like a tuning knob, right? I can increase it positive or I can increase it negative, right? And they give you some values for the breakdown voltage. So if this is positive, let's think about what's going to happen. If this is positive, this is in forward bias and this is in reverse bias, okay? At a certain point, well, 6.8 volts, this will allow current. Okay, and so what you get is something that looks like this. If this voltage increases, it has to overcome the reverse breakdown voltage and the forward voltage, and then it'll allow current to flow. If this voltage is negative, well, what happens? It's essentially just always blocked by A, right? So this is blocked by diode A, okay? And so I wrote down here what's going on. When voltage positive, diode A is in forward bias, diode B is in reverse bias. When voltage negative, diode A is in reverse bias and diode B is in forward bias. Okay. All right. What about this situation? So I got two diodes in parallel. This one happens to be a Zener diode. And in this case, when the voltage is positive, what happens? Diode A is in reverse bias, diode B is in forward bias. Essentially, this current is going to follow this path, right? It doesn't even care about the Zener diode. Okay, when this is negative, then what you're going to have is a pressure over here. The current's just going to flow through diode A like as if it's a normal diode and get blocked by B. And so what you would see is something like this. And I believe this is in your homework one, a similar problem in your homework one, where it's just two back-to-back normal diodes, right? If we go to the extreme, this is basically a vertical line with a very minimal forward voltage, right? Okay. All right, not too bad. So let's look at a load line analysis where we actually put this into a typical application, right? So we have a Zener diode, and really when you're using it, you're kind of putting it in backwards. You notice how I have the cathode on the top here. So imagine I have a voltage source here, and this could be, you know, kind of noisy or anything, right? I have a resistor, and let's say the output voltage I want to be regulated to a certain value. In fact, that value would be regulated in this case to the back voltage of this Zener diode. Okay, remember this is a pressure relief valve. Okay, notice I'm consistent with my what do you call it, the convention. I put the negative with the bar and the ID going the same direction as this arrow. Good. But I want you to think, before I even like dive in any math and load line analysis, I want you to think what's going on. Imagine if this voltage was, or this back voltage was 5 volts and this was 10 volts. Well, what's going to happen? This is going to want current to go through, right? And then it's going, or sorry, if this starts at 0 volts, this is going to be blocked. No current's going to flow at all. But as I increase, eventually what's going to happen is once this surpasses the back voltage, this is just going to allow current to flow through here and not allowing the pressure on this side to build up. Okay, and so this will maintain whatever back voltage is here, designed in this Zener diode, and this one can kind of vary up and down. Okay. So I kind of said, you know, I stated here what I just said. Even if Vs varies, V naught stays constant, and it's constant to the breakdown voltage. Okay, and so what we're going to do is we're going to combine our 250 analysis, basically our nodal Ohm's law, with our new Zener diode curve. We did this last lecture, and so let's be careful though. Notice I have the minus signs. Let's double check. So ID equals to, so if this is a ground, minus VD. Right? So let's just kind of do this slowly so that, right, I have this. This node voltage, if I have a ground here, this node voltage is either positive V naught, which is equal to minus VD. Can you guys see that? right? So right there, that's actually the voltage from here to here is actually minus VD. And the voltage here is still, the node voltage here is actually VS. So if ID is pointed in this direction, if I follow that arrow, ID is equal to minus VD, right? Minus VS over R, okay? Where this is R, okay? And that's why you get that equation. Good. I'm going to break it up so that I have this as my Y and this is my X. So I just distribute the R. And again, I get this Y equals MX plus B form. And look at this, by KVL, I actually should write it here. By KVL, V naught is equal to minus VD, okay? All right. So what does that look on our Zener diode curve? Okay, so on our Zener diode curve, I have my Zener diode curve drawn, and notice this is a negative sloped line with a negative y-intercept. So I have something like this, okay? All right, so I know there's a lot of text on here, but let me just walk you through what's going on, all right? If I change certain values, like for example, this VS, notice this actually goes down, right? It starts going down the curve because I have a negative value, right? Okay, because this point here on this line is actually negative VS over R, and this is negative VS for the x-intercept. So actually increasing VS will actually pull this down, right? And maybe you're a little confused as to, well, why is it going down when the previous lecture is going up? Well, remember, this ID is actually defined as opposite of the direction of the previous problem from last lecture, right? So this ID is actually going that way. That's why. Okay, so what is that telling us? What this is saying is the intersection between this ET250 nodal Ohms law line and our new Zener diode curve is where this thing behaves, right? And so don't lose the intuition that this is a pressure relief valve. And at low voltage, we are here. And so that means it's operating at no current, right? No current. If this voltage is lower than the breakdown voltage, no current. And you're seeing that here. No current, no current, no current, no current, no current. If I increase the voltage, what happens? This line shifts down. And now what do you notice? The current starts increasing, right? But the voltage, right? This voltage here is equivalent to the breakdown voltage, right? So VD, which is going that way, is the same as V naught, which is here. So this V naught is always constant, and it's equal to this breakdown voltage, okay? So in other words, let me summarize. As long as the voltage source is above the Zener diode breakdown voltage, the diode operates at negative VB, okay? And due to KVL, V naught would equal negative of the negative VB, which means it's positive VB, which is constant, okay? So hopefully that this is kind of more of the mathy part, but again, if you just follow the intuition, hopefully this connects, right? Okay, good. Let's look at an example that kind of puts this load line analysis with some numbers. So now we have the same situation, exactly the same situation, except for a load resistor, right? So we got a VS, an R, a Zener diode, and we've just added a load resistor, and now we have a load current. Okay, we still have V naught, we still have VD, and notice again, V naught and VD are opposite in sign. Okay, and ID is still pointed with the same direction as the Zener diode. Okay, now let's say this is actually, we have some numbers on here. This is 15 volts and this is 100 ohms, all right? And let's say that the Zener diode reverse bias voltage is 10 volts. So that means we want this thing to be regulated at 10 volts, okay? Now the question is, what is the smallest resistance here such that this is 10 volts, okay? And so what's the problem? Now, this time I'm not varying the 15 volts, I'm not varying the R, these are staying constant. I'm actually varying this RL. Okay, let's kind of go through a thought experiment. If this RL is too small, and let's go to the extreme. Let's say this RL is like a short, which means it has 0 ohms. Well, what is this? What's happening to the Zener diode? Well, it's shorted, right? And if this is shorted, what's the voltage across the short? 0. So now this V naught is 0, and it's not our desired 10 volts. This is like a high load, right? Because it's pulled a lot of current and it's drooped the voltage, right? And so this Zener diode isn't helping us, right? And we just can't maintain the voltage because we're asking for too much current here. So what does that mean? We need to actually increase some resistance here. We can't request so much current. So you can imagine if we keep increasing the resistance here, there will eventually be a point where this V naught will be 10 volts. And so that's the question. What is that resistance when when we get to that 10 volt? Well, let's go to our Zener diode curve and load line analysis, and we can see what happens, right? Okay, so here's our Zener diode curve, and you can imagine if we were here right at that point, where we have no current, right? We have no current. Then the diode voltage is negative 10 volts, which means the output voltage is 10 volts. So this is going to be the magical point right there. This is going to be the magical point where you're just at the minimum, right? You're just at the minimum voltage or resistance such that you're going to get 10 volts on this output. Okay, let's keep going. So how would we find that? Well, at that magical point, we can make an assumption. We actually can do this. If we're at that magical point and there's no current flowing through this diode here, then we have a very simple situation. We have R, RL, and VS. I actually took the Zener diode out. And now we can go back to our ET250 analysis, right? We have a voltage divider, simple. So what is the voltage divider? V naught equals RL over R plus RL times VS. And I have a positive because positive and positive, good. At this point, I go, okay, well, solving for the RL such that this current in here is 0, what do I get? Well, just a little bit of algebra, bring this to the other side. Okay, good, did that. And then I want to solve essentially for RL. So what am I going to do? I'm going to pull out the RL times V naught, good. I'm going to bring this RL over, so I have a minus VS, and then I'm going to bring this R to the other side, good, and then solve for RL, put this in the downstairs. Excellent. So now I have an equation for RL as a function of R, VS, and V naught. And I can plug these in. So R, what is that? 100 ohms. V naught is, well, what do we want? We wanted it to be 10 volts, right? And what is VS? It's 15 volts. I can plug all those in and I get 200 ohms. And so just to recap, this is the number for this resistance such that this voltage is 10 volts and I get no current going through this guy. Okay, no current going through this guy. Okay, so this is just hopefully a simple example of the load line analysis and our new Zener diode concept. All right, okay, see you in the next lecture.